Well, in fact, the solution is staring us in the face if we look at how we represent the GDP of America normally. Let's assume we're interested just in the first 3 digits. We don't want to know it any more accurately than 15.7 trillion. Usually you wouldn't write it out in full like we've been doing. In any ordinary text, you just write something like 15.7 trillion as a word. Let's separate that out. The 15.7 tells us what digits we actually care about. The fact that it's 15.7 and not 20.2 is important. And then that trillion tells us how big the number is. In other words, how many zeros go after the 15.7. Now recall from the integers module that the number of zeros is just the power of 10. A trillion is a million million, it means 12 zeros, so it's 10 to the 12. So we can write the GDP of America as 15.7 times 10 to the 12. Now there's just one minor change I'd like to make to that. If we're going to write numbers in this form, we probably want to agree a standard place for the decimal point. And in fact, the usual convention is that we put the decimal point after the first digit. So that makes the number 1.57 times 10 to the 13. If you're confused about that last step, think that I've just divided the 15.7 by 10 and then multiplied the 10 to the 12 by 10, and the two actions cancel out. That's what is known as scientific notation or exponential notation. The reason for being called scientific notation is that science often deals with very big numbers like this, so this way of writing numbers is most commonly used in science. And if you haven't guessed already, the reason I'm telling you all this is because scientific notation is, in principle, the way floating point numbers are stored on your computer. There are some details we need to work out, and there's the very big technical difference that computers will be using binary, not decimal, but the principle is the same. Now I should give you some more terminology. The number 1.57 that tells you what the first digits are is known as the mantissa, or sometimes as the significand. And you'll recall from the types of data module when we covered powers that the 10, the thing that you are raising to the power, is called the base, and the number you are raising it to is called the exponent. So in general, a number is represented as plus or minus the mantissa times the base to the power of the exponent. Let's just show you a couple of other examples of how to write numbers in scientific notation, just to make sure we understand the principle. Let's start really simple and look at the number 3. Now remember, 10 to the 0 is just 1, so we can write 3 as 3.00 times 10 to the 0. I'm putting 3 digits in the mantissa just so for the sake of picking a number of digits that is consistent in all the examples, but it doesn't actually really matter how many I put in. Let's look at a slightly bigger number, 30. We want the decimal point after the 3, so it has to be 3 times something. Obviously 30 is 3 times 10, so the something is 10, or 10 to the power 1. Now let's try out a fraction, 0.03. Well, you can probably see that's 3/100ths, or 3 divided by 100. Now remember, when we looked at powers in the types of data module, we said that in general 1 divided by 10 to the n is 10 to the minus n. So 1/100th is 10 to the minus 2. And the answer we want is 3 times 10 to the minus 2. Now, when you're working out minus powers, there's a trick to get the answer quickly. Just count the number of leading zeros. That means the zeros at the front of the number before the first non-zero digit. Make sure you include both the 0 in front of the decimal point and any zeros after the decimal point before the first non-zero digit. Make that number negative, and that's the power of 10 you need. And you can see that works for 0.03 because the answer is 3 times 10 to the minus 2, and you have 2 zeros there. Finally, let's convert the mass of a water molecule into scientific notation. Counting the zeros before the leading non-zero digit, there are 26 of them. So the mass is 2.99 times 10 to the minus 26 kilograms. And you can see it's much shorter to write the number this way, so that's definitely how you would normally write it. And the great thing about scientific notation is how little space it takes up on a computer. For the moment, let's continue thinking in decimal and look at the GDP of America again. And let's think about what you would need to store if you were storing it in decimal. Well, obviously you need to store the Mantissa, the value 1.57. You also need to store a sign to say it's 1.57 and not minus 1.57. And you need to store the number 13 that says the exponent is 13. And you also need the sign for the exponent, but the way it works, that's actually embedded into the exponent itself. Provided you understand that this is how numbers are being represented, that's actually all you need to store. Notice that you don't need to store the 10, the base, since it's presumably understood that that's the base in every number. And also, because we've agreed on a standard place to put the decimal point, after the first digit of the Mantissa, you don't need to store that either. So you can see the total amount of data and the number of bits you would need to store this data is tiny compared to trying to store it in fixed point form. And the other great thing is that we have potentially reduced the problem of representing the number in a misleading form by trying to store all those zeros explicitly, because we're not trying to store them now. The only disadvantage is that we have 3 different things to store, which is rather more complicated than with integers where you just had one thing to store. Exponential form is actually so important that most high-level languages will build in an ability to display numbers using it. However, there is a twist. You can't put superscripts into unformatted text. So to work around that, the usual way is to write an E and then put the exponent and the plus or minus sign to say whether the exponent is plus or minus after the E. So in that way, the GDP of America would look like this, 1.57 E plus 13. Now, just to illustrate this, I've written a quick C# application that illustrates displaying numbers in scientific notation. To just show you what it does, we will quickly compile and run it. And you can see it's asking you to tell it what number you want to be displayed. And we've started off with 1. And it's also asking you how many digits you want to be displayed in the number. So if we go ahead and display it, you see 1 is the 4 digits you've asked for, 1.000, and then it's in exponential notation, so it's 1, and the E plus means times 10 to the plus 0, so that's 1 times 10 to the 0. If we try, say, 10, and this time I'll only ask for 3 significant digits, then we see 10 is 1 times 10 to the 1, E plus 01. Or if I try something like 0.4. 0.4 is 4 times 10 to the minus 1, and that's E minus 001. There's not really that much code to show in this. All I'm really doing is on the number, I'm simply calling toString on it to display it as a string, and passing it a format, which is a string basically telling the computer how I want the number to be displayed.